In this section, we're having a closer look at the domain and the range of a function. To describe a function completely, we need the function rule that describes what happens with the input to yield the output, and we need also the domain of the function. Normally, the domain, or most commonly, the domain is just R, but there are two typical sorts of functions where the domain is not equal to R. One is when x occurs in the denominator, and the second one is the x occurs under a root. Well, if the x occurs in the denominator, the function is not defined for values of x where the denominator is 0. And if the x occurs under the root, the f function is not defined for values of x where the expression under the root is smaller than 0, negative. Let's look at some examples. 1 divided by x to the power 1 divided by x plus 3, that's f of x. So let's find the domain of the given function. Well, we have to look at, since x occurs in the denominator, where is x plus 3 equal to 0? So we see that's true when x is equal to minus 3. So for that x value, the function is not defined. So the domain of f is then just all the values, all of x, so r, without the value minus 3. Now try to solve the other examples. Here come the results. Here we have x under the root, so the problem is if x minus 5 is smaller than 0, which means if x is smaller than 5, and this means the domain is whenever x is larger than 5 or equal to 5, so we can write it as all the x's where x is larger or equal to 5, or just as we're using the interval notation from 5 to infinity. In this example, the x is under the root and in the denominator. That it's in the numerator is not important. So the 4 minus x here has to be, we have a problem if 4 minus x is smaller or equal to 0. So by adding x, we get we have a problem if x is larger or equal to 4. And this means that the domain are all values of x where x is smaller than 4. So we can write that in this way, or again using interval notation, the interval from minus infinity to 4 excluded. In this example, the x occurs in the denominator. Again, the numerator is not important. So we have a problem if the denominator here is equal to 0. This means if x is equal to minus 5 or equal to 2. So our domain is all values of r without minus 5 and 2. And the last example, the most difficult one, here we have a problem if the expression under the root is negative, so x plus 1 times x minus x is smaller than 0. To find out where this is true, we instead just set the expression equal to 0 and solve it. We get these two results, and now we use the sign diagram, which means we draw the number line here, and below the line we will mark the values of x, and above the line the values of the expression x plus 1 times x minus 6. And we start with marking those x where the expression is 0. So we found that before for minus x being minus 1 and x equals 6, the expression is 0. That's what we found here. And now all that we have to do is to find out now we've separated the whole number line in 3 regions, the one to the left of minus 1, the one between minus 1 and 6, and the one above 6, all these values. And what we know is that the expression here will be positive or negative always for the whole of these 3 regions. So we have just to find representatives for which we find out is it positive or negative, and then we know it for the whole region. So let's start with the this area here, for example, we could insert -10. So -10 plus 1 is -9. -10 minus 6 is -16. -9 times -16, well, minus times minus is plus. That's the only thing that I was interested, so I know in this region it is positive. Then let us take a x value here in between. The simplest one is just 0, somewhere here. When we insert, we get here 1 times -6 is negative. So this whole region, in this whole region, the expression is negative. And when we insert now a number from this region here, for example 10, we get 11 times 4, 44 is positive. So we found out this expression here, x plus 1 times x minus 6, is negative in this region here from -1 to 6. And the function is defined wherever the expression is larger or equal to 0, which means when x is lower or equal to -1, or x is larger or equal to 6. And written in interval notation, this means the area -infinity to -1 including, united with the area 6 including until infinity. Now let us have a look at the range of a function. This means all the possible output values of the function. With our current knowledge, it is virtually impossible typically to find the range of a function if it is given by its equation. However, if the function is given by its graph, we can very simply find it, the range, namely by looking at what y values occur on the graph. Let us look at this at some examples. Here we have a function f with it given by its graph. So we see, for example, the function value 2, y, appears. F of x, there is a x, so that f of x is 2, namely this y value. There's also a y value for 3.5, namely this one and this one here. It's enough that there's just one. We find also a the y value -2.5 on the graph here and here. We would find a y value of 17 when we are up here on the graph, somewhere here, because this goes on to infinity. However, we will not find a value of y equals -4 on the graph. There is nowhere the graph that a point on the graph with y value -4. So from that we see now the lowest y value that occurs here is obviously -3. So all y values that occur are from -3 to infinity, and we get that the range is -3 to infinity. Try to do the same for the next next three examples. Stop the film, and here comes the result. By the way, in this context, you don't have to care about whether the brackets are closed or opened. We can't really read that off, obviously, except for infinity, where it's always opened. But otherwise, whether this point is now really on the graph or not anymore, the -3 here, we can't know. So don't care too much about that. Okay, the result here for this graph, we see for a y value of -4, we find points. For a y value of -1.5, we find points. And also for -1, we find 1 point. But already for -0.5, y value of -0.5, there is no point on the graph with that y coordinate. So we see the range, the occurring y values are just from -infinity here until -1. Looking at this example here, we see that the y value -3 does not occur anywhere, and also the y value 4 does not occur anywhere. When we look, actually, for example, the y value 2 occurs many times, or the y value -1/2 here occurs many times, and it becomes obvious what y values do occur. Well, those between -1 and 3. And last example here, again, a number value, for example, already 1/2 here does not occur on the graph. However, 3.5 occurs, or 1.2 here occurs somewhere here, and so on. So we see all values, all y values larger than 1, they occur on the graph. So we get from 1 to infinity.